Hi all. Before we start, I would like to give a shout out to Sebastian Lag and his YouTube channel. He creates a lot of interesting content around Unity and game development in general. In fact, the controller 2D in this video has been inspired from Sebastian's own implementation of controller 2D. So please check him out and subscribe to his channel. So without further ado, let's begin.
Hello. Welcome back to the third video of our platformer creation series. In this video, we'll start working on our Raycast controller to help us detect collisions or lack thereof. Let's head to our Raycast controller 2D in Visual Studio. Let's get rid of the default code and create a collider reference. Public collider 2D collider. Let's create our awake method and let's pass in our box collider 2D component reference. Now let's create a struct called Raycast origins. So our collider being rectangular in nature, there are quite a few origin points we could consider. So the most obvious ones would be the vertices. So that is top left, or top right vertex, bottom left and bottom right. And apart from these, we could also consider the midpoint of our edges. So the left edge midpoint, the right edge, the top edge and the bottom edge midpoint. And lastly, it would be also useful to consider the center of our box collider as an origin as well. So let's create public vector 2 top left and top right as well, and similarly we could create for our bottom left and bottom right. Now for our left edge and our right edge, then our top edge, center and bottom edge as well. So these vectors are presently empty, but they need to store position values and they need to be updated every frame, as the position of these would change depending on how the player moves. So for that, let's create a method public void update raycast origins, and let's reference our bounds from the collider, and let's shrink our bound ever so slightly such that our raycast origins would start from inside our player object as opposed to right at the edge. And we can call this skin width, and let's multiply it by -2. So we are starting from inside our player object, and based on the direction which we pass to our raycast, it would go from the origin to that direction up to a certain distance. We'll provide a very small value to our skin width, so 0.15 should be fine. Let's reference our Raycast origin structure in the class, and inside our update Raycast origins method, let's pass values for all our origin vectors. So bottom left would have minimum x value and also minimum y value. Bottom right, on the other hand, would have the maximum in our x value, that is the rightmost x value which we have, and similarly it can have minimum in the y value since it is at the bottom. Now top left would start with minimum in the x but would have maximum in the y, that is the topmost y position which is possible to us, and similarly top right would have maximum x and maximum y. For our left edge, we would take minimum in the x and center of our y, and for the right edge, maximum in the x and center of our y again. For top edge, we'll take center in the x but maximum in the y. For the center, it is straightforward, center x and center y, and bottom edge would be center x and minimum y. So now that we have our origin values from the collider bounds, we would also need to raycast at an offset from these bounds so that we can cover the whole perimeter of our collider. To explain this, let's head back to the whiteboard. So this box would represent our collider, and let's mark down our raycast origins, and let's draw an object which the player plans to collide with. So when the player reaches the edge of the collider, our raycast would detect the collision and our velocity would be set to 0. But in other cases where our colliding object is not perfectly positioned to hit our raycast perpendicularly, our player would pass through the object, and that is undesirable. So we would have to place our raycast origins at all points across the perimeter of our collider bounds, but that is a very inefficient solution. So what we can do is place some more origin points at an offset from our raycast origins. So if we consider the top right vertex, we would like to place few more origin points across the right edge starting from our top right vertex at an offset. So this offset right here is what we need to calculate now. From the collider bound, we can get our length of the edge, and we can pass in the offset distance between two origins. So the length of the edge divided by our offset distance and rounding it to an integer would give us the count of the origin points we need to generate across this edge, and we can follow the same logic across the other three edges as well, and in this way we can cover the whole perimeter of our bound in order to detect collision. So let's head back to Unity and let's create a new method. So we'll go public void calculate ray spacing, we'll call it, and here let's get our bounds again and also shrink it by skin width into 2, negative of course. And now let's get our width and height of the bounds. So now to store our count across the horizontal and vertical edges, let's go up and create two variables. So we'll type public integer horizontal ray count, and we can hide it in the inspector since we don't need to show it. And similarly, we'll create one for our vertical ray count and hide it in the inspector as well. So back in our method, we can say horizontal ray count equals mathf dot round to end, and here we'll say bounds height divided by distance between rays. So of course distance between rays is not a variable as of now, so let's fix that. So we can say const float distance between rays equals 0.2. So this is our offset between two origin points. So now for our vertical ray count, we can say vertical ray count equals mathf dot round to end bounds width this time divided by distance between rays. Now that we have our count, we need to create a variable to store the ray spacing value between any 2 points. So for that we can type horizontal ray spacing equals bounds height divided by horizontal ray count minus 1. And similarly for the vertical ray spacing, it would be bounds width divided by vertical ray count minus 1. So for our ray spacing variables, let's make them public as well and hide them in the inspector for now. So the ray spacing has to be calculated only once, that is at the beginning of our scene. So let's create a start method, and from here we can call our calculate ray spacing.
So let's add an attribute hide in inspector for our collider variable as well. So now we have most of what we need in this class. So if we go back to our architecture from the first video, so you would remember that there is a class controller 2D which inherits from Raycast controller, and now that we have created our Raycast controller, it's time that we create our controller 2D now, and inherit from Raycast and use its properties to provide collision detection for our player in the controller 2D script. So in our controller 2D, let's create a structure called collision info. In here, let's create four boolean variables and make them public. First one is above, then below, left, and then right. So these would represent our collisions horizontally as well as vertically in all the four primary directions. Let's also create a reset method in here to reset all the four boolean variables to false, and on the top let's create a reference to our structure. We'll name it collision info with a small c, Now let's create a move method which is public, and let's call our update raycast origins method from the raycast controller 2D, which we inherit from, as this needs to be updated every frame. Later on we'll also call our move method from an update method so that it runs every frame. And let's also call our reset method from the structure, since we also need to reset our variables every frame, because we need to detect the collision and then update it back again on every frame. Let's head to our player movement.cs and create an update method here. And before we add anything here, let's head to our player attributes.cs and create a reference to controller 2D in our player info structure, and also initialize it in the constructor to null. Back in player movement.cs, let's comment our log statements for now, as we don't need them. And let's copy this code which gets our player instance using the instance id and paste it in our controller 2D in our awake method. So we are getting an error. It says cannot identify player attribute. So let's fix that. Let's copy our code from player movement. Let's take this protected player attributes PA and let's paste it in our Raycast controller. And since controller 2D inherits from Raycast controller, it also would take in our reference and the error should be resolved. So back in our controller 2D, we do get another error. It's to do with the initialization of controller 2D into our player movement reference, which is not possible. So let's fix that. We need to replace player movement with controller 2D and the error should be resolved now. Let's get rid of this comment. And now back in player movement.cs, we can make use of our controller 2D reference. We can say pa.pi.controller2d and we can call our move method inside our update method. Now that we have our functions hooked up, let's create a few variables to actually enable our player to move. So let's create a vector 3, we'll call it velocity, and let's initialize it in our constructor. So let's make use of this velocity variable as a parameter in our move method. So let's include it and multiply it by delta time, and also at our receiving end in controller 2D we can name it as move amount. So along with velocity, we also need a vector to read our input. So in player attributes, let's create a vector 2 called directional input. And now let's go to player movement and hook up our directional input to the input value which we receive from our event. Since set directional input method is subscribed to our input event, we can just pass the input parameter into directional input. Let's also include this as a parameter in our move method. Now at our receiving end in controller 2D, let's call this as input. Now let's create a method called horizontal collision and we'll reference move amount as a parameter, since we want this value to persist and not get duplicated. This method will be responsible for handling all our collisions across the x-axis. Let's also call this method from our move method and pass in move amount as a reference parameter. We need to create an integer in our collision info structure to store our direction which the character is facing. We'll call it face dir and we'll retrieve its value from move amount's x value. We'll say move amount.x is not equal to 0. If that's the case, we'll use mathf.sign move amount.x and we'll pass it into our face direction integer. So now in horizontal collisions, we can say float direction x equals collision info dot face direction and float ray length equals mathf absolute of move amount dot x plus skin width. So our length would depend on the x value which we receive from the input, which will be from -1 to +1, and we'll add in skin width because we start from inside our collider at an offset of skin width, so we need to include that as well, so that we don't end up with a ray length which ends inside our collider. And for x values of move amount, which are extremely small, we'll create an if condition here. Mathf dot absolute of move amount dot x. If it is smaller than skin width, we'll say ray length equals 2 into skin width. So we multiplied by 2 because once for our skin width offset, so that our starting point starts from skin width and comes out of the collider, and the other as a replacement for the small x value of move amount. So let's start a for loop from 0 to the horizontal ray count, and we can say vector 2 ray origin equals, we'll create a ternary operation here. We'll say direction x equals -1. If that's true, raycast origins dot bottom left vertex. So that means we'll start from the bottom left vertex and make our way up, creating intermediate ray origin point. And if that is false, that means we are going to our right, that is direction x equals +1. Then we say raycast origins dot bottom right vertex. So let me open up our whiteboard and quickly illustrate this. If our directional input is -1 on the x, we'll start from bottom left vertex and we need origin points across this edge on our left, and if it is 1, that is our input in the x value, so we'll start from bottom right vertex and make our way up along the right edge. So back in the code, we can say ray origin plus equals vector 2 dot up, since we need to go upwards from the bottom vertex, into horizontal ray spacing into I. I is for our increment and horizontal ray spacing is the value which we need between two origin points on our edge. So to illustrate this in our whiteboard, suppose the whole equation vector 2 dot up multiplied by ray count into I, we'll call it simply as up for the illustration purpose, and I equals 0, then our whole equation would amount to 0. But if I equals 1, we'll get our first offset origin point across the left edge, and similarly if I equals 2, we'll get our second, and similarly I equals 3, we'll get our third origin point, and this would continue till we reach the last ray count value in our for loop. So back in our code, we'll say raycast hit 2d hit equals physics 2d dot raycast, and in the parameters, first we need our origin. We'll type ray origin, and for our direction, we need it to be either of the two horizontal directions. So we'll say vector 2 dot right into direction x, and for our distance, we'll pass in ray length, and at last for our layer mask, we'll type collision mask. Of course, we need to first create this layer mask. So let's go to the top of our class. We'll say public layer mask collision mask, and there we have it. So this layer mask is required so that our raycast hits are only detected for the objects present in this layer. So we can include all our platforms, walls, etc. in this layer mask. Now we also need to draw our raycast in the scene so that it is visible to us. So we'll say debug.drawRay starting from ray origin and pointing towards vector 2 dot right multiplied by direction x, and we'll give it a color red. And now below that we can say if hit equals true, then we can check for our hit distance, and if that equals 0, we can continue to our next ray origin. If not, then we will say collision info dot left equals the value which we receive from the condition direction x equal -1, and similarly for collision info dot right, we'll set the value which we receive from the condition direction x if it equals +1. Now once we have manipulated our move amount reference value, we can simply pass it into our translate method. So in move method we can write transform.translate move amount. So now in the similar way we can also create a method for our vertical collisions, but before that we need a few variables in our player infrastructure. So in player attributes.cs, first we'll create public float gravity, then we need two float variables, one for the maximum jump velocity and another for the minimum jump. Let's also initialize all these variables. So gravity equals 0, max jump velocity equals 0, minimum jump velocity equals 0. And we would also need few publicly exposed parameters which we can control from our inspector in Unity. So at the top of our class we'll mention three variables: max jump height, we'll give it a default of 4, minimum jump height equals 1, and the third is time to jump apex, we'll give it zero point 0.4. And now in our player movement.cs, let's make use of our publicly exposed variables to generate values which can be stored in our structure variables, that is gravity, max jump velocity and min jump velocity. So let's open up our whiteboard once again and let me try to explain the mathematical reasoning behind this. So let's just first note down what we will be providing as a user. So that is max jump height, min jump height and time to jump apex. And then let's note down what we will be solving for, that is our gravity, max jump velocity and min jump velocity. So why we are solving for gravity especially is that it's not a very intuitive value to be taking in from the user, but on the other hand a user will surely be able to tell how much does he want the player character to jump. So max jump and min jump are an intuitive value that can be provided, and so is time to jump apex. So this means the amount of time afforded to the player character to reach the pinnacle of the jump height. And now let us note down the formulas which we would need. The first one is delta movement equals velocity initial into time plus acceleration into time square by 2. And the second is velocity final equals velocity initial plus acceleration into time. So let me just zoom out on the board and make some space to illustrate our approach. So suppose we have our player character here on the ground. So we know that its velocity on the y-axis at that point would be 0, and as we press our jump button, the character's goal would be to reach max jump height, and the time it would take is time to jump apex, both of which we have already provided as the user. So all we need now is to use this formula, the first one, to get our acceleration. So delta movement is nothing but our max jump height, and velocity initial would of course be 0 because we start with 0 velocity when we are jumping from the ground, into time plus acceleration into time square by 2. So let's solve for acceleration. So max jump height equals a into t square by 2. Now we can convert this into 2 into max jump height equals a into t square. Finally we can say 2 into max jump height divided by t square will be equal to our acceleration. So that is the acceleration which we would require when making a jump, but what we need at the moment is gravity, which is downward acceleration. So if we were to multiply our formula with -1 and we'll replace a for acceleration with g for gravity, so we would get g equals negative of 2 into max jump height by t square. So next up we have max jump velocity to solve for. Let's use our second formula for this, which is velocity final equals initial plus acceleration into time, and velocity final is nothing but our max jump velocity, and initial of course we know is 0 plus acceleration into time. So we can say max jump velocity equals absolute value of our gravity, so that would get rid of the -1 which we had multiplied previously into time to jump apex. So lastly let's calculate the min jump velocity. So Let me just drag the whiteboard down and make some space at the bottom. So for this we'll use a new formula, which is velocity final square equals velocity initial square plus 2 into acceleration into displacement. So to illustrate this and why we need minimum jump velocity is that when the user taps the jump button but does not hold on to it till the jump is completed, that is till the player character reaches the max jump height. So in such scenarios we would like the player character to start falling from a lesser height, that is we want our gravity to act sooner. So if we were to replace and add our variables to this formula, we would get min jump velocity square equals 0, that is velocity initial square, since we start from 0 velocity in the y-axis, so that's 0 plus 2 into, so now acceleration again can be replaced with absolute value of gravity, so 2 into gravity into min jump height. So min jump height would act as a displacement. So solving for min jump velocity, we would get min jump velocity equals square root of 2 multiplied by absolute value of gravity multiplied by minimum jump height. So now that we have derived these three formulas, let's implement them in our code. So back in Visual Studio, we'll open up player movement.cs. We'll create a start method here and we'll say pa.pi.gravity equals negative of 2 multiplied by pa dot max jump height divided by, and we'll use the pow function here, so mathf dot pow, and in brackets we'll say pa dot time to jump apex comma 2. So this basically says to multiply time to jump apex with itself, and in the next line we'll calculate for max jump velocity, which equals mathf dot abs, that is absolute value of gravity multiplied by time to jump apex, and third is our min jump velocity, which is mathf dot square root of 2 multiplied by absolute value of gravity multiplied by min jump height. And below this let's add a log statement and let's just print our gravity and our jump velocity. We'll go for max jump velocity. As we know, anything below that would be our min jump velocity, and that would be determined by how long the user holds on to the jump button. So all these might be a little confusing now, but it would all make sense when we implement them into our character movement. So let's do that now. Let's go to the bottom of our class. We'll create a method called calculate velocity, and we'll say float target velocity x equals directional input x multiplied by move speed. So move speed of course does not exist yet, so we'll create that. Let's go to player attributes and we'll create a serialized field of type float move speed, and we'll give it a value of 6 for now. So back in our player movement.cs, in the next line we'll say velocity x equals, and we'll use a damping function. So we'll go mathf dot smooth damp, and this needs 4 parameters. So first is our initial velocity, so we'll give it velocity dot x. Next is our target, so we'll say target velocity x from the previous line, and then we need an velocity smoothing reference, so we'll just create a variable and reference it here, say pa dot pi dot velocity smoothing. This of course does not exist yet, so we'll create it. And the last is our smooth time, which is the time it would get to cover the distance between our initial and target velocity. So here we would like to pass two different values based on whether we are in the air or on the ground. So let's use a ternary operation. We'll say if collision info dot below is true, we'll pass in a new variable acceleration time grounded, and if not, we'll pass in acceleration time airborne. So let's create both of them as well. For the acceleration time grounded variable, we would give a smaller value, so let's go with 0.1. so that would mean our movement would be faster as we have afforded it less time, and for time airborne, let's increase it slightly to 0.2. So there would be a bit of drag, I would say, when the character moves sideways while airborne. Okay, we seem to be getting an error here. Yeah, we were missing an x over here. So now for our y value and velocity, we'll say velocity dot y plus equals gravity multiplied by time dot delta time. So now let's call this method an update at the beginning. So what's happening here is calculate velocity will manipulate our x and y values based on the parameters which we have given, like gravity and max jump height, min jump height, and that particular velocity would be passed as parameter to our move method, and we'll also get our directional input as a parameter. So here in the move method, we'll receive it as move amount, which will reference to our horizontal collisions and also vertical collisions, which we'll create now. So let's paste this method below horizontal collisions and let's remove the throw statement. So same as the direction x and ray length we had in horizontal collisions, we'll create a direction y float and a ray length float variable. And similarly, we'll use a for loop, and this time we'll iterate till vertical ray count instead of horizontal, and our ray origin would check for direction y. If it's negative, we'll start from the bottom left vertex and make our way to the right end, and if it is positive, that means our character is going up. We would start from the top left vertex and make our way till the top right, and again we'll add on to the value of our ray origin like we did for horizontal collisions, and also we'll now calculate our raycast hit 2D, and instead of checking for the x values we'll replace y everywhere. So vector 2 dot up will be multiplied by direction y, and we'll also draw the ray on our scene. And now if we detect a collision, so if hit is true, our move amount should equal to the hit distance multiplied by the direction which we are facing, and of course we'll subtract skin width from the distance because we have been starting our rays from little inside of our collider at a value of skin width, so we would need to subtract it before we pass into our y value for move amount. So that would take care of the vertical distance that our character can travel when it is nearing a collision, and also at the point of collision we would set the ray length same as that of our hit distance, and we'll manipulate the below and above collision info boolean values. So if direction y is equal to -1, that is the character is falling down, we would set the below as true, and since this is inside of our hit condition, we also know that it has landed on a platform when falling down, so we can set the below to true. And also if our direction y equals 1, that is our character was going up when it collided, that is our hit is true, we would set the above boolean value to true. So now that we have set our boolean values for above and below based on our collisions, so back in player movement in update, we can say if collision info dot above or collision info dot below is true, let's set our y velocity to 0. So this would stop our player character from passing through the floor or the roof of our platforms. So before we test this, there's another change we should make. So in controller 2D, let's put an if condition around our vertical collisions call in the move method. We'll say if move amount dot y is not equals to 0, only then we would allow vertical collisions to be checked, so that we can avoid some unnecessary calculations which might not be required when we are already on a platform. Now finally in player movement, in our on jump input down method, we can say if controller 2d dot collision info dot below is true, then we can set our velocity y to our max jump velocity. So back in Unity, before we test our game just yet, let's disable the two additional players which we had created earlier for now. And let's open up project settings, head down to script execution order, and let's add two scripts here. First is player manager, and we want to place it such that it runs before our other script, so we'll give it a negative value so that it goes above the default time position. And the other one is player attributes, and this as well we need to run it before the default time but after the player manager. So let's put in between those two. So we need both player manager and player attributes to have loaded before our other scripts, because these two are our foundation based on which all our other scripts interact. Also, in our physics 2D setting, let's change our simulation mode from fixed update to update. So let's create a platform for our player to stand on. Let's scale it by 10 on the x-axis and place it at a -5 position on the y-axis. And let's remove the mesh collider and add in a box collider 2D. Let's give our platform a layer. So add layer, we'll name it obstacle, and let's add it to our platform. Also in our player, let's attach our collider 2D that we created and set the collision mask as obstacle. Okay, now so let's play. Let's move our character on the x-axis. That seems to be working fine. Let's jump. That too looks alright. So everything looks fine. Let's give our platform a material. So we'll create an obstacle folder. We'll right click, create, choose material. We'll name it obstacle as well. Let's select the albedo color. We'll go for a dark green and let's make it an unlit color. And now let's drag our material onto our platform. So that looks great. Let's zoom out our main camera so that we can look at our play space much better. We'll test our player character a few more times. So the gravity is working fine. The max jump looks good as well, and our min jump seems to be working too. Now why don't we introduce another player object on our scene. So let's just enable the player 1 and see how it behaves. Okay, so I have tested it for some time and I have noticed two issues in particular. The first one being, if we have a wall in front of our player and if we were to approach the wall and try to collide with it, you would notice that the player instantly does a weird jump and reaches the top of our wall. So this is just a miss on our end in our horizontal collision. So let's quickly fix that. So back in our code, let's head to our controller 2D in horizontal collisions. Inside our hit detection, if hit equals true, so we can write move amount.x equals hit distance minus the skin width into direction x. So this will allow our controller to calculate the distance at which our collision would occur, and it would reduce our move amount x value based on that, and right when we collide it would be 0, and in this way our player would stop when it touches a wall. So that's fixed. So the second issue is with our skin width. If I were to play and zoom in on our player and focus on our bottom edge here, you would see that our rays don't exactly start from the left edge and end at the right edge. That's because our skin width is actually quite huge, and which is causing issues with our ray distance calculation. We want our skin width to be even smaller so that our rays are very close to our vertices so that our collision detection is even better. So back in Raycast controller 2D, we'll just decrease our skin width value. Let's make it 0.015, and now if we were to go back to Unity and play, you would see that our skin width being smaller, our rays are much closer to our vertices, and this is much better. So this is pretty much it for this video. I took quite long making this one, but it was interesting and there was a lot of stuff to learn. For any one of you who have stick till the end of this video, I appreciate you all greatly and hope this was helpful for you and you enjoyed it as much as I had making it. I'm unsure where to take this video series next, but inverse kinematics seems interesting to me at the moment, and maybe we could make a 2D IK character, but I would like to hear from you guys what you would like to see. So until next time, cheers.